8.4, Example 8. Before we dive into Example 8, I first want to go over the comparison test theorem. And this comparison test theorem is going to allow us to compare different functions, and in order to find if certain integrals converge or diverge if our integral is too difficult to work with. So let's first go over the definition of what it is. Let f and g be continuous on the interval a to infinity, where 0 is less than or equal to f, which is less than or equal to g, for all x greater than or equal to some a value. All this means is that one function is always bigger than another function. So from this theorem, we're going to get two things. The first thing is that if f of x converges, if g of x converges. So if the bigger function g of x converges, it's going to force the smaller function to converge. The second thing is we get the bigger function diverges if the smaller function diverges. So if the smaller function diverges, it's going to make the larger function diverge. And again, from the first thing, if the bigger function converges, the smaller function must converge as well. So before we dive into our example here, I want to go over a graph and kind of show you what I mean by that. So here I have two functions, e to the negative x and e to the negative x squared. And you can see after a certain point that the green function is always above the blue function. So if the green function converges, then the blue function has to converge. If the bottom function diverges, then the green one also has to diverge. So example 8, does the integral from 1 to infinity of e to the negative x squared dx converge? So we can't actually evaluate this integral because there's no simple formula that we can use to integrate this. There's no u sub, there's no by parts. So what we need to do is find a more simplified function that we can look at. So if e to the negative x squared is our function, we need to find a g of x such that our g of x function is always larger than our f of x function. So what we're going to do is we're going to go ahead and look at our graph again. So here you can see that e to the x isn't necessarily always bigger. E to the negative x is smaller between 0 and 1. However, I only care about values as we get large. So you can see that e to the negative x is always bigger than e to the negative x squared. If we zoom in, you can see that the green is still bigger than the blue. And if I zoom into values, even bigger values around 20, it's going to take me a while. You can see these y values are getting very small. So it's just going to take a little bit of zooming. And here we go. We can finally start seeing something happen. And here we go. We can see our green function is still larger than our blue function for insanely small decimals. So we have that the green function e to the negative x is larger than e to the negative x squared for large x values. So we can see that e to the negative x squared is always smaller than e to the negative x, and they're both above 0 for x is greater than or equal to 1. So if the integral from 1 to infinity of e to the negative x converges, then the integral from 1 to infinity of e to the negative x squared converges as well. So this means that we get 0 is less than or equal to the integral from 1 to b e to the negative x squared dx, which is less than or equal to the integral from 1 to b e to the negative x dx. And what we want to show is that when we let b to go to infinity for this, we get a number. So we're going to take the limit as b approaches infinity, the integral 1 to b, e to the negative x dx, and we're going to go ahead and work this out. So when I do the antiderivative, I get negative e to the negative x from 1 to b, and it's the limit as b goes to infinity. So the limit as b goes to infinity, negative e to the negative b minus e to the negative 1. So I'm just going to clean that up a little bit before I go ahead and plug in my b value. I get e to the negative 1 minus e to the negative b. So it's the limit as b approaches infinity, 1 over e minus 1 over e to the b. So we take the limit, and this goes to 0. So my answer is 1 over e, which is approximately 0.368. So what we need to do now is write out a conclusion because we started with a theorem. So we were trying to show something using a theorem. So we have 0 is less than or equal to e to the negative x squared, which is less than or equal to e to the negative x for x values greater than or equal to 1. So now what we want to do is go ahead and integrate. So 0 is less than or equal to the integral from 1 to infinity e to the negative x squared, integral 1 to infinity e to the negative x, again for the x is greater than or equal to 1. So we're going to write those as proper integrals. So it's 0 is less than or equal to the limit as b approaches infinity, integral 1 to b e to the negative x squared dx is less than or equal to the limit as b approaches infinity, integral 1 to b e to the negative x dx. So now that we have that, we're going to go ahead and work out that right side. We show that the right side is going to end up being 1 over e, which is about 0.368. So this shows that the integral from 1 to infinity e to the negative x squared dx is always less than or equal to 0.368. So we've shown that it reaches a number. So thus, the integral from 1 to infinity e to the negative x squared converges.